This is 5.2, study of logarithms. You have covered logarithms in a previous class, so this should be a refresher. So the very first thing we want to start off with is, for x is greater than 0, the definition of what a logarithm is, log of base a of x equals y, if and only if, that's what IFF stands for, x equals a to the y power. And if you look at that, you're like, well, what does that even mean? Well, again, notice something you should remember how to do this. You take the base and you raise that to the y power. So literally a to the y power and equals x. So you're going counterclockwise. So you start with the base, raise it to that y power, and that equals x. And so how does that help? Well, look at this. If I ask you to evaluate log base 2 of 32 without a calculator, well, that's looking for some number here. So 2 to some power equals 32. Well, that's 2 to the 5th power. So 2 to the 5th power is 32. So I know that this actually is 5. Okay? Without using a calculator, I can check. I know the answer is 5. Well, this one right here, 4 to what power equals 2? Well, I know that 4 to the 1st is 4. So it's got to be smaller than 1. So I know the square root of 4 is 2. Well, I also know the square root of 4 is the same as the 1/2 power. So I know this is to the 1/2. So 4 to the 1/2 power equals 2. Now this one, you need to become familiar with it. I've said it multiple times. So here, log base 3 of 1, what does that equal? Well, 3 raised to what power is 1? Well, anything to the 0 power. So 3 to the 0 is 1. So this equals 0. 3 to the 0 power. Again, go in a counterclockwise motion. Now, if I was using my calculator, so on your calculator you have a log button, and so here you have if I just wanted to evaluate log of 10, and then you're and I want to remind you, if I don't say a base, it's an automatic 10 base. So you can check this. 10 to the 1st power is 10. So you didn't need a calculator on that. So log of 1/3. So log of 1/3. Log of 2.5. And log of -2. Now, when you get this one, you're like, well, why did it get an error on that? Remember back on the definition, x has to be greater than 0. So you can't take a log of a negative number. So you can see, depending on the instructions, all the other ones, you can go to and look at it, depending on, let me clear that off. So depending on if I want 2 decimal places, 3 decimal places, whatever the instructions say, but you can get all those other answers. Decimal places 477, and then 0.398. All right, now if I wanted to graph a log, again, this is basically what I just did. I made an XY chart. That's really what I did. I evaluated it and found out what it would be. So, you can do that if you want, or go to y equals and just log of x. And if you want to push graph, it's going to... Now, by the way, sometimes graphs can be deceiving because it looks like it starts right here, and then it looks like it goes like that. But I want you to notice what happens when it gets... Let me erase that because that's not right. If you look at the table, and we've done this on other problems, and notice, by the way, the table 0 there's an error. So in other words, we can't have 0. Remember, it has to be greater than 0. So there is an asymptote right there. And at 1, it's 0. At 2, it's slightly above it. And if we go, let me jump ahead. Like at 10, we know it's 1. Now, what happens let's look at what happens at 0, between 0, and let's count by 0.1. So at 0.1, So we're talking about a very tiny number. It's at -1. It's right here. And at 0.2, it's still negative. At 0.3, 0.4, so notice it's approaching 0. And if you got even smaller numbers, like if you started counting by 0.01, like we're talking about a really tiny number. So at 0.01, it's down here at -2. So notice, and if you kept doing 0.001, so this is going to get really, really close. Let me use a different color here. It's going to get really close to an asymptote. It's really close to this line. But again, according to the graph, it looks like it starts there. Well, it doesn't start. It just gets so tiny close to that, it doesn't graph it well. If we zoomed in and you could see this, like if we change the window just from x minimum to 0, x max 1, x scale we counted by 0.01. So you can see what's happening. It's literally just barely going above that. And you can play around with the window. I'm just going to take it back to normal. You can play around with it, but it literally does gets really close to that asymptote right there, and it goes like that. Now, all log functions are going to look like that. Okay, all log functions. So unless it's transformed or translated left or to the right or up or down, but it's always going to look generically like that. So the properties of logs, so here I have log base A of 1 equals 0. Again, if we go counterclockwise, A to the 0 equals 1. See, it makes sense. All right, A to the first is A. So if you know that counterclockwise, A to the x power equals A to the x power. So one way to, if these ever match, then the answer is the exponent. Okay, that's one way to say that. Might be doing that, but that counterclockwise motion is going to work. So, again, if this matches the base, then the answer is A. This last problem, if log base A of x equals log base of y, that means x equals y. In other words, again, if the log A and log A, if these equal one another, then that means these have to equal one another. That's going to come in handy when it comes to solving equations. So if I ask you to solve this, well, again, notice what I just got done saying. If log base 3 of x equals log base 3 of 12, that means x equals 12. So here I have log base 10, log base 10. That means the 2x plus 1 equals 3x. And then you can solve it. X equals 1. Here, log base 4 equals log base 4. That means x squared minus 6 equals 10. And then you can solve this, x squared equals 16, x equals plus or minus 4. Now, when you check this answer, be careful, because some of you might say, well, I thought x can't be -4. You can't graph a, like when x can't be -4, when you plug it in, you can't take a negative of a logarithm. Okay, so on this problem, you can always check your answers, but make sure you can't take a logarithm of a negative. So even if I plug in a negative or a positive and I square it, see, this is still going to be a positive answer. Okay, so I still can have positive and negative on that one. All right, so if I was graphing the log function, we've already done it. So graph y equals log of x, we've already done that. But I want you to consider like a different base. If I consider this green graph, so we already looked at this graph right here. Let me change the settings here. So I'm going to start at 0. I'm going to count by ones. So the table for this one, again, you can't have anything negative. So let's graph 1, 0, and 10, 1. Whoops, 10, 1. 1, 0, 10, 1. And we know it hugs the asymptote right here. That's the normal log function. Vertical asymptote right there. Now, log base 3 of x. So if you look at your calculator, if you push the math button and log base 3 of x. And if you notice the graph, you're like, well, it looks the same. Well, notice the values of this. I mean, most log functions are going to look exactly the same except actually the values of it will be different. So if you notice these, let's do this one in blue. So we still have 1, 0. We have 3, 1, 9, 2. And then notice the red. Notice the red, what's happening is you're shifting 4 to the right. And then 2 up. That function, let's plug that one in. So this is, it's still base 10. So we've still got log parentheses x minus 4, close your parentheses, then plus 2. You notice the graph on this. Notice what's happening here. You have on this red one, and again, you have to know that you still have it, it's being shifted 4 spaces, so the asymptote is being shifted 4 spaces. And so it may look like it ends there, but it doesn't. Okay? And you have to trust the, what you know about logarithms. So at 4, there's an error, and automatically I know at 5 it's at 2. And let's just do, I'm trying to find the 1. 14.3. That's too high. So let me just do 8. But again, you notice it hugs that, and like that. It always hugs hits right next to the asymptote, and that's where it goes. It starts at really close to the asymptote, and then it goes goes further out as it goes away from the asymptote. So the natural log, ln, so whenever you have a log base e, remember e is approximately 2.718. So log base of e, that's actually the same as ln. So if I ask you to evaluate ln of 2, so again, the ln button's right here, so ln 2, ln 3.1, ln of -1. And guess what we're going to get? We're going to get an error. Remember, it has to be, all logs have to be greater, has to be greater than 0. Can't even equal 0. All right, and then if we had to graph that, again, the same thing. All log functions are going to look the same. So remember, natural log is log, just a different base. So natural log of x, if I graph that, that's going to look very similar to it, okay? So it's the same idea. You graph it, XY chart, and don't forget about the vertical asymptote. Now, the properties of the natural log are very similar to what we did already. So again, you may want to pause the video and look at these properties, but they're very similar to what we did earlier. I would suggest on some of these, think of this as log base e. See, the 0 power is 1. Not like you necessarily have to memorize these, just remember that natural log is log base e. If I ask you to write these in log form, well, again, this is e to the 4th power, so we want log e. Remember that counterclockwise motion is what we're talking about. So e to the 4th power to the 4th power is 54.598. This one right here, e squared, we're writing it in log form. So log e, again, this is to the 2nd power, e to the 2nd power equals 7.389. And you really could, because it's log base e, you could just write ln. If you wanted to do it that way. All right, that's the first topic, 5.2, dealing with logarithms. The next section also has to deal with logarithms as well. Make sure you know the basic idea of what a logarithm is and how to write it in exponential format.